All right, so you'll recognize this as the key to the review document for Chapter 14, Exam 4. And we're going to get through 14 and 15 today. And I've picked out some problems that I think are particularly useful for understanding the material. So let's get started. Number one, in fact, which of the following is a conjugate acid-base pair? All right, Chapter 14. Acid-base pair. What's required for an acid-base pair? If we take our generic acid, and react it with water, which is actually what it does in solution. And this is the acid, and this is the base for an acid dissociation. Then we have the conjugate base of the acid and the conjugate acid. Okay, so the acid-base pair here is this acid and that base. Now, what do they have in common? The A part of the acid and the base are identical. They must be identical. Otherwise, that one condition disqualifies any others. Then, if the A's are identical, let's see, who else showed up? Okay. If the A's are identical, then the transition from acid to the conjugate base can only be accomplished by the loss of one proton. So if we're missing one proton from here to here, that's a conjugate base of this acid. Of course, as long as the first condition is met. All right, so let's look at number one in terms of those two rules. All right, we have this one and this one. H2SO4 and SO4 minus. This one. And we have this one. And then, of course, we have more than one. So when you have a situation like that, you got to look at all of them and see if you do have more than one conjugate acid-base pair. All right, let's take the first one. What's the A part of this acid? It's right here. Okay. So if you remove that proton, do you get a chloride? No. We get a hypochlorite ion. So that one cannot be an acid-base pair. How about this one? There's the A part. You would think this is saying that that's A minus. And this would be A over here, but what's happened? It's lost two protons. So that one can't be an acid-base pair either. What would it take for this one to be, what conjugate base would be applied to this acid? One proton loss. That would be the conjugate base of this acid. How about this one? This one's a little trickier. Ammonium ion and ammonia. You have lost one proton. That's true. We met the second condition already. What would be the A part? This is the A part, that whole thing. And it's over here also. All it has is just an extra proton added to it. So this is an acid-base pair. How about this one? We got to see if this one is true. If this one's true, then E's the answer. But what would you, if this is an acid, if you lose a proton, what do you get? Water. So that one can't be it either. So in fact, C is the only possible answer for number 1. All right, let's see. Better check these off as I go. Okay, how about number 2? Let's see, let's walk this up just a little bit. The hydrogen sulfate, or bisulfate ion, bisulfate is a trivial name that's grandfathered in from ancient times. HSO4- can act as either an acid or a base in water solution. In which of the following equations does HSO4- act as an acid? All right. So if we're starting with this one, how would it act as an acid? Well, when it reacts with water, it transfers a proton to the water molecule and leaves behind now we have this as an acid, and its conjugate base is SO42-. This would be the base, and that would be its conjugate acid. All right. What if it were acting like a base? Well, let's see. What's the answer there? 2. The only one that fits that one is D. But what if we let that act as a base? When it reacts with water now, water becomes the acid. So according to Bronsted and Lowry, a proton must be transferred from the acid to the base. Oops. So now this is the conjugate acid. Oops. Come on now. There we go. Okay, and there's the conjugate base for this acid. That's what it would be if we treated bisulfate ion as a base. All right. How about 3? Which of the following is the equilibrium constant expression for the dissociation of the weak acid HOCl? It's fairly straightforward. If you're starting with this one, right, how would it behave as an acid? Right? It's got that proton up front. That's why we put it there, so we could dissociate. All right? We're going to write it shorthand version. We're going to leave water out of it. Why is that valid? Because water is not part of the expression. Water is a pure liquid, so it wouldn't be part of the equilibrium expression anyway. Right? So if we just treat it as a dissociation, like that, right? And the K will be like any other equilibrium expression, this times that divided by that. By the way, what's the name? What are the names here? Well, obviously, that's proton. This is the hypochlorite ion, polyatomic ion. So that means this is hypochlorous acid. All right, so that makes A is the correct answer for this one. All right. Let's see, how about number 6? Here we go. So if we have a solution in which the pOH is 12.1, how would it be described? Look at our choices. Acidic or basic or neutral, or very acidic or very basic. So my way of thinking, it's easier to determine acidity, basicity, if you have the pH rather than the pOH. Because, well, I think in terms of neutrality is pH 7, which in fact would be pOH also. But if the pH is less than 7, you're acidic, and if it's greater than 7, you're basic. All right, so let's say we have pOH equals to 12.1. What would be the pH? It's a really simple calculation, right? So there's your pH, 1.9. That is definitely acidic. It's not neutral because it would have to be exactly 7. So if it's acidic, then how acidic is that? That's very acidic on the pH scale. In fact, OSHA, Occupational Safety and Health Administration, classifies anything with that pH as corrosive. I think it's pH of, I think it's 2.5 or less is corrosive, which means it can damage your skin very quickly. All right, so that was A for number 6. Okay, let's see. How about 7? Which of the following indicates the most basic solution? In this case, the best approach is also to go for pH. Then you can compare apples and apples. The way it is now, you've got a hodgepodge of different values and expressions that's difficult to compare. So we've got one of them that's already pH, right here, D. So let's convert the rest of them to pH. Right? For A, the hydrogen ion concentration is 1 times 10 to the minus 10. Right? So pH would be negative log of 1 times 10 to the minus 10, which would be equal to what? 10. Right? You can ignore the 1. So base 10 right, base 10 would be a power of 10, would give you the negative log of that value. How about B? pOH is 6.7. We did one like that just a minute ago. 14 minus 6.7 equals what? As 7.7 3 pH. So we got this one, got this one. How about C? OH minus equals 7 times 10 to the minus 5. Okay. POH is equal to, I need my calculator for this one. So we have 7, 10 to the minus 5, take the log of that, change the sign, 4.15. And then the pH would be 14 minus that. 9.85. Okay, and D is already calculated for us, 4.2. And E is at least 2 of the solutions are equally basic. Well, is that true? These two are close, but they're not equal, right? So E can't be in. All right, so which one is, back to our original question, which one is the most basic? The one with the highest pH, right? So there, there. A would be the highest pH of all these, the most basic. All right. How about 8? Which of the following solutions contains the strongest acid? Right? How do you determine the strength of an acid? Right? If you have your generic acid, like that, and you're given a K value for that, K represents that expression, right? So the larger the K, the more protons you have relative to the concentration of the original acid. So larger K means stronger acid in chemical terms. It's not the equilibrium position, it's the equilibrium constant that determines the strength of the acid. Okay, so now let's look at our Ks. And by the way, we have one of these acids here, the B acid, has 2 K values. Which one do you pay attention to? Well, it depends on how close they are together, right? 1K, Ka1 is for the first proton. Remember, the second proton dissociates less easily. And most of the time, the second K value is pretty far away from the first. In this case, it's true. There's 10 to the minus 5, 10 to the minus 12. Right? That's 7 orders of magnitude, which is a long way off. So in this case, the pH is determined by the first K. If, however, you run across a polyprotic acid in which the K values are very close to one another, even if they're like 10 to the minus 2 and 10 to the minus 3 for the second one, then you might have to consider the second proton. But as long as they're this far apart, 7 orders of magnitude, you can assume that the pH is determined by the first K. Let's see, let's get everybody in here. 1, 2, 3, 4, 5, 6. That's right. Okay. Okay, so in that case, we can focus on the first K's, or the only K, depending on the acid. And you just look down here and focus on the power of 10 first. Here's 10 to the minus 10. Here's 10 to the minus 5. That's a stronger acid. It's got a larger K value. Here's a 10 to the minus 5. All right, so we get to that one and say, okay, which one's stronger? Then you have to look at the coefficient. So 7.9 is bigger than 1.8. So B is stronger than C. And it's also stronger than D because that's 10 to the minus 8. Then you get down to this one, HF. 10 to the minus 4 beats everybody. So E would be the strongest acid. It has the largest K value for the first dissociation constant, and the second dissociation constant for B is inconsequential. It's too small. All right, that was 8. How about 9? Which of the following statements are true? Should have been is are, is/are. Is true if there's only one of them, are if there's more than one. All the statements A through C are false. That's what E says. So we got to look at each one. Well, D also says at least 2 of the statements are true. So we do have to look at A, B, and C. Those are the unique ones. And D and E are combination answers. So we need to look at A through C and determine if the statement, each one of these statements, is true. All right, for A, the pH of a strong acid is always lower than the pH of a weak acid. Well, first of all, do we determine acidity by low pH or high pH? The lower the pH, the more acidic the solution. That doesn't mean that you have a larger K value, or by inference in calculation, a larger K would be a smaller pK. So the pH of a strong acid is always lower than the pH of a weak acid? No, that's false. For instance, if you had a 0.001 molar hydrochloric acid solution, and you had a 10 molar acetic acid solution, I think it's fairly safe to assume that the acetic acid would have a lower pH. You could calculate it, of course. This one's simple. You'd have to do a ice table for this one, probably. But that just illustrates the fact that there's a difference between equilibrium position and equilibrium constant, and by inference for acids and bases, a weak acid can have a very low pH. Depends on the concentration. It's a definition of weak and strong. Okay, so A is false. How about B? The pH of a solution can never be negative. Really? How do you determine pH? What's the calculation? Negative log of the hydrogen ion concentration. If you get the right value for hydrogen ions, you can have a negative pH. For instance, let's say the hydrogen ion concentration does happen to be 10 molar. That'd be pretty high, of course. Right? So what's the negative log of that value? Well, what's the power of 10 that gives you 10? right? That's the definition of a log. The power of the base that gives you the number. In this case, it's 1. 10 to the first power equals 10. Right? So that implies that. And then you take the negative. And, well, the answer to this is -1. The power of 10 is 1, negative that is 1. So you can't have negative pH. So B is also false. So let's see what C has to say. All right. C is for a conjugate acid-base pair, Ka equals 1 over Kb. Is that true? No, it's false. Let's look at it. What's the Ka for acid dissociation? Right, so we have our acid there. So the Ka for this would be hydrogen ions, conjugate base, divided by the acid. Okay? What would be the Kb for this reaction? Well, I assume that what they're looking for is the Kb for the conjugate base. Right? So the conjugate base would be A minus. In this case, we do have to react it with water. In which case you would form the acid there, plus this. Now what's the Kb for that expression? Well, you have HA OH minus divided by A minus. Okay, so there's the Ka, there's the Kb. Is the reciprocal of that? What is the reciprocal of that? The reciprocal of that is A minus over HA times OH minus. Now, if this expression is correct, then that should be equal to this. Obviously, it's not. Okay, so what is the correct expression? Remember, Ka times Kb equals Kw. So in that case, Kb equals Kw divided by Ka. Okay? That would be a true statement. That is a false statement. So, all three of them are false. That's why E is the answer. Because it says all those statements, A through C, are false. Okay, that was number 9. Let's see, I'm going to skip to number 11. All right, so we're going to take the conjugate acid-base pair to the next level. Say we have a triprotic acid, phosphoric acid. So, when that acid dissociates, in other words, transfers a proton to a water molecule, what does it look like? Well, we're going to abbreviate it. We're just going to use the dissociation. You know, on second thought, let's write it out correctly. And I'll show you why in just a second. So when this stepwise dissociation takes place, we have this one reacting with water and producing there we go. So there's the acid, there's the conjugate base. Then what happens? Then this conjugate base becomes the acid for the next dissociation. And you're left with this one. Okay. Then for the third dissociation, we take this polyatomic and react it with water. And you get PO4 3 minus. Okay, those are the three steps in the dissociation of phosphoric acid. So let's look at conjugate acid-base pairs. All right, so each one of these is acid, and then the conjugate base is here. So that will be an acid-base pair, H3PO4 and H2PO4 minus. Let's see, do we have one of those? Yep, B. So this is associated with B. How about this one? H2PO4 minus and HPO4 2 minus. That looks like C. Talks to that one. How about HPO4 2 minus and PO4 3 minus? HPO4. There we go. A is this one. Okay. I think we found one that was not a conjugate acid-base pair. Right? We've got A, B, and C, so D is probably wrong. Yes, D is wrong. Why? Because it implies that you lost 2 protons in the process. And conjugate acid-base pairs don't do that. 1 proton at a time. So D is false. Well, how about E? Is E a conjugate acid-base pair in this reaction? Yeah. In all 3 of them. Acid, base, acid, base, acid, base. So E is also a conjugate acid-base pair for this dissociation. In fact, it's a conjugate acid-base pair for every acid dissociation. All right, that was number 11. Okay, how about 12? For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? We alluded to that one earlier. Right? So when does the second dissociation affect the overall pH? When Ka1 is very close to Ka2. Then the second dissociation affects the pH. So in which case do we have that? Well, let's see. Here's 10 to the minus 2, 10 to the minus 7. That's too far away. That's 5 orders of magnitude between the first and the second one. No effect. How about this one? 10 to the minus 4, 10 to the minus 8. That's 4 orders of magnitude, 10,000 times. No effect on the pH. How about this one? 10 to the minus 4, 10 to the minus 9. That's 5 orders of magnitude. What's that? 100,000 times. Here's one, 10 to the minus 3, 10 to the minus 4. That's only 10 times away. Plus, look at the coefficients. Right? What is 1.8 times 10 to the minus 3? 1.8 times 10 to the minus 3 in standard notation. Right? 0 point. 1, 2, 3. 1, 2, 3. There we go. There. How about the second one? 9.3 times 10 to the minus 4. So 9, 3. Like that. Oh, sorry. One more. There we go. Okay. Notice when you look at it this way, you can see how very close they are. Actually, it'll look better if we line up the decimals. There, like that. Right? So how much of a bump would it take for this one to be close to that one? Well, let's see. Tens, 100,000s, 10,000s, 100,000s. 700,000ths would put us near 1, and then another 8 would put us right at that value. These are very close together. So any acid that had these characteristics, A, Ka1 and Ka2, that close together, the second dissociation will have a significant impact on the overall pH. Let's see, there we go. Keep my board from walking too much. That was 12. Let's skip to 16. Trying to get as much of these under. If we get to the end and then we've still got time, then we can come back and look at some others. But these I definitely want to get to. 16. Here we go. Which of the following will give the highest pH when dissolved in water to form a 0.1 molar solution? All right. So we're looking for the highest pH out of this group. E, yep, E. All right. Strong acid. Right. So let's 0.10 molar. Right. Strong acid. Let's just pick one. Right. So it'll be more concrete. How about hydrochloric acid? That's a strong acid. We could use nitric acid to work just as well. Hydrochloric is our strong acid. How about a weak acid? A weak acid would be maybe acetic acid. Okay. How about the potassium salt of a weak acid? All right. So let's take our weak acid and make a potassium salt out of it. That's what that means. Oh, excuse me. That's a sodium salt. There we go. Potassium salt of acetic acid. How about potassium salt of a strong acid? All right. Let's make the potassium salt of that one. Okay? How about the ammonium salt of a strong acid? So let's make the ammonium salt of HCl. Ammonium. There we go. Now we have concrete examples of each one of these. And we're looking for the highest pH, which would be the basic one. This one you can solve by rule of thumb because they're all the same concentration. All right? So this is going to be a very low pH, right? It's a strong acid. That's a low pH. We're looking for highest pH. How about this one? This would be a medium pH because it's a weak acid. It won't be a particularly high pH. It will be less than 7. Right? It will be acid. How about this one? Let's skip that one for a second. How about this one? What would be the acid-base reaction that would produce this salt? A strong base, KOH, and a strong acid, HCl. Those types of reactions produce neutral solutions. All right? Okay, let's go back to this one. Weak acid, strong base, KOH and acetic acid makes a basic solution. So this pH would be greater than 7. How about this one? This one is a strong acid and a weak base. Ammonia plus hydrochloric acid is the reaction. This pH would be less than 7 based on our rule of thumb. Right? Strong acid, weak base, pH less than 7. So C would give us the highest pH. In fact, it's the only one that's greater than 7. All right. Now we could have done this abstractly, use generic A's and so forth in there. But I think it was easier to comprehend if we actually give it real components. All right, so that was 16. Let's scoot down to 19. Oops, too far. There we go. All right, solid ammonium acetate. Oh, excuse me, a missing part of the question. Select the answer. Here we go. See that? 17 through 20. Select the answer that best describes an aqueous solution made from each of the following substances. We might as well do all of these, right? Since it's the same concept, and practice is always good. Extra practice never hurts. So let's say for 17, solid sodium nitrate, and you put it in solution. Okay. Acidic, basic, or neutral? Or can't tell? I think we can tell. Right? Derived from a strong acid? Derived from a strong base? That's neutral. About 18. Solid sodium carbonate. Okay, put that in solution. All right, what is it derived from? Base, weak acid, right? The carbonate ion. So what would the acid be if it were derived from that? Right, HCO3 minus. Okay, So that means it would be basic. How about 19? All right, let's see. Now we've got a weak base and a weak acid, right? Solid ammonium acetate. Ammonium acetate. Put that in solution. What is it derived from? Well, it's a weak acid and a weak base. So we have to compare the Ka for the acid and, well, actually the Ka for this acid and the Kb for this base. Right? Because this is the actual reaction that would take place in aqueous solution. You would react this acid with water. How effectively does it transfer a proton to water? Or you would react this anion with water, and how effectively does it extract a proton from water? Right. So with our rule of thumb, I'm making this distinction. With our rule of thumb, we look at the origin of each side, right? The origin here is a weak acid. The origin here is a strong base. But when you're looking at the K values, you have to look at the actual species that's reacting, right? This is a base. It's no longer considered derived from a weak acid. This is a strong base, right? Because acetic acid is a weak acid, so that would be a strong base. This would be what? It's derived from a weak base, so it would be a strong acid. But we have to consider the K values. When you're putting them both together, actually how strong or how weak are they? Well, as it turns out, the Ka for this acid is 5.6 times 10 to the minus 10, and the Kb for this base is 5.6 times 10 to the minus 10. They're equally strong in their own respect. So this solution would be neutral. Nobody wins. And you can prove it to yourself. Just go into the lab, get yourself some ammonium acetate, mix up well, any solution, 10th molar solution. Check the pH. I guarantee it will be 7. Now that, of course, assumes that these K values are correct. Right? You know how tests are. They make stuff up. So if those values are correct, then the solution will be neutral. All right. So that was 17, 18, and 19. Let's go to 20. Let's see, did I get any extras here? No, that's it. Everybody accounted for. 20. Solid ammonium perchlorate. Oh, that's part of the same group. It just went to a new page. All right, so we'll do 20 also. Ammonium perchlorate. So what is the perchlorate? All right. In this case, you can look at it either way, either as a quantitative comparison of Ka and Kb. So the Ka for this is 10 to the minus 10, And the Kb for this one is 10 to the minus 21. It's a very weak base. Okay. So this is a much stronger acid. It's still a weak acid, but it's stronger than ClO4 minus. So that would make the solution acidic, correct? Ka wins. That's acidic. Rule of thumb says this is derived from a weak base, NH3. Perchloric acid is a very strong acid. So the rule of thumb says the solution would be acidic. And another way to prove that this is a strong acid is just look at the Kb. The Kb says that that ion doesn't want a proton, right? Because it's so small. It does not want to extract a proton from water. That means it was derived from a strong acid. Right? So you can look at it a couple of different ways. The answer is still acidic solution. All right, now we can move on to 22. Which factor listed below is most important determining the strength of an oxy acid? What is an oxy acid? Got to be an acid, right? It also has to have oxygen in it. One, maybe more. And then some, let's say B. So this group right here is technically your A group. And you'll have one or more oxygens in that group. That's an oxy acid, which means what? It's always polyatomic. All right, what determines the strength of that acid? This is by definition, actually. The strength of that acid is determined by the number of oxygens. Okay? The more oxygens you get, the stronger the electronegative pull on electrons. So the electron density then is drawn away. Like for 3, there's your proton. The electron density is drawn away from that proton, which makes it more and more positive in nature, which means it's easier to leave. You weaken that bond as you add more oxygen. So the more oxygens determine the strength of the acid. That's why this trend is toward acid strength is up toward perchloric acid. Perchloric is the strongest acid of this group. Chloric acid is pretty strong. Chlorous acid is actually weak, and hypochlorous acid is very weak. All right, that was 22. 24. Why don't we look at 23 also? They kind of fit together, 23 and 24. Right. So 23 says, which of the following would produce a basic aqueous solution? All right. Let's see, what do we have to deal with here? B4O10, KCl, CO2, and NH4Cl. And then none of these. That's a possibility. If they all produce acidic solutions, then none of them produce basic solutions. All right, so what is this? They're both nonmetals. One of them's an oxygen, and it falls under the category of acidic anhydrides. It was that one little section in our chapter, acidic anhydride. Okay. Now, the name tells you what type of reaction will undergo if you put that in water. Okay. You will add the water back to that molecule. And let's see, I may have painted myself into a corner here. What I would expect to get from that is H3PO4. So let's see. Try to balance it. Well, let's just say it's not balanced, but that's what you get. Actually, it may not be PO4, it might be PO3. I bet it is PO3. Anyway, when you rehydrate it, you get an acid. And that solution is going to be acidic. How about this one? Right? Derived from strong base, strong acid. It's always neutral. How about this one? This one, when you add water, you get H2CO3. Carbonic acid. In fact, I think that one is balanced. So that one's acidic also. Right. How about this one? Derived from a strong acid, rule of thumb, strong acid, weak base, acidic solution. So all of these are acidic. That's why E is the answer. None of them are basic. All right, so let's scoot down to 24. Which of the species below, when dissolved in water, will not produce a basic solution? Which means it's either neutral or acidic. So 24, not produce a basic solution. All right. What do we have here? We have oxygen with a nonmetal. That is an acid anhydride. Produces, actually this one is fairly easy to figure out, H2SO3. Sulfurous acid. Okay, so that one's acidic. It will not produce a basic solution. That's true. How about NH3? That's a weak base. Right? That produces a basic solution. How about BaO? A metal oxide that dissolves in water is a basic anhydride. So when you add water to this one, you get barium hydroxide. In fact, I think that's balanced. Yeah, that's balanced. So that's basic. And barium hydroxide, right? By inference. So the only one that produces an acidic solution in this whole group is A. E can't be right because one of them is correct. That's your acidic solution. It's not basic. All right, let's see. What's next? We're good on time. How about 25? In fact, I want to look at 25 through 27. There we go. We're talking about Lewis acids and bases here. Right. So what do you need to have a Lewis acid? A Lewis acid is an electron pair acceptor. And a Lewis base, of course, is an electron pair donor. Okay? So, let's look at these examples and see if we can answer the question. Which of the following species cannot act as a Lewis base? Cannot be an electron pair donor. Right? How about this one? It's got lots of electrons right there. So that can be a Lewis base. How about B? OH. That can donate an electron pair. How about C? That's methane. Methane is like this. And each one of these hydrogens has its duet. The carbon has its octet. It does not want to donate or accept, for that matter, any electrons. So this one, well, actually, if I answer the question correctly, cannot act as a Lewis base. No, that's correct. Right, this one cannot act as a Lewis base. What about the others? Let's go ahead and be thorough. Hydrogen sulfide. It's got a couple of lone pairs up there it can donate. And E. What is it? Ammonia. Ammonia is like this. Hydrogen there, hydrogen here, and a lone pair up there. So ammonia can donate also. It can be a Lewis base. Methane is the only one that's not a Lewis base. All right, let's see. 26. Cannot act as a Lewis base. Oh, we got another one here. Well, okay. Notice that we've already covered the ammonia, right? Ammonia can be a Lewis base. We got that one covered. NH2 minus, due to the fact that it has that extra charge, that can donate electrons. That one can donate electrons. That one can donate electrons. All of these can be Lewis bases. The ammonium ion is electron deficient as a base, as a Lewis base, because all of the hydrogens have their duets, and nitrogen has its octet, and on top of that, it's got a positive charge. It doesn't want to give up electrons. If anything, it wants to gain electrons, which means that the correct answer is E, but also that ammonium acts like a Lewis acid. All right, that was 26. Which of the following species cannot act as a Lewis acid? All right. Notice we've got positive charges here, all the way down. That one, that one, that one, that one. Those are not electron donors. If anything, they would accept electrons, which means that they're all Lewis acids. The only one that can donate electrons and act as a Lewis base, which would answer the question, is the H- ion. Cannot act as a Lewis acid because it's already got an electron, right? It's got one proton. This is an extra electron, right? This one has one proton, one electron. It's already got one electron. If you do this, now you got two electrons. Where are they going to be located? Oops, sorry. They're going to be in that orbital. There's no more room for them, right? So this cannot act as a Lewis acid, right? It will not accept electrons. All right. So there, 29. In this reaction, we're still on the topic of Lewis. For 29, we've got this reaction. Solid. And then we've got SO2 gas. And then we've got calcium. Sulfite. Solid. All right. The key to this problem is looking at the answers, because that tells you what it wants to find. Which one acts as a Lewis acid and which one acts as a Lewis base. Okay. So let's define our terms here. Notice that this is an this is a covalent compound, so it's not going to break apart. It acts as a unit. But this is an ionic compound. It has calcium ions and oxide ions. So each of those can act independently of one another. So what would this one be? A Lewis acid accepts electrons. This could be a Lewis base, donating electron pairs. What would this one do? Well, it depends. Well, also when you get over here, you got calcium 2+ and sulfite 2-. Right. So this could be a Lewis acid, and this would be a base. All right. So in this reaction, what has happened? This group has accepted electron pair. In order to bond with that oxygen, it accepted an electron pair here that was donated by this base to this Lewis acid. And the fact that it had to accept those electrons here to make that 2- there means that this is the base and this is the acid. So that would make the conjugate Lewis base this group, and it has no conjugate Lewis acid because it's part of that. Right? That doesn't work, not for this one. Okay, so let's look at our choices. Calcium acts as a Lewis acid. That's true. And SO3 2- acts as a Lewis base. Well, technically that's true, but during the reaction, we're focused on this side, right? In order to transfer electrons, we have to look at this side. So A is not the best answer, even though it's true. It's not the best answer because SO3 2- is not reacting with calcium, right? It's on the other side. It's already happened. Right? So in order for that to happen, you have to focus on this side. So A is not a good answer. O2- acts as a Lewis base. That's true. So B and C would also be true. Sulfur dioxide acts as a Lewis acid. That's true. The calcium acts as a Lewis acid, not in this reaction, right? Because it's already in the compound. It's not a reactant with the base and the acid. It's a reactant with this acid. Right? So this base reacts with that acid. That is the best definition of what's happening here, B. Of course, calcium oxide, the whole thing doesn't act as a Lewis acid. It's only part of it that acts like the acid. This one, it could be an acid, but it's not in this reaction. Right? There's a distinction there. What's actually happening in the reaction? And as always, the best answer is the choice. O2- acts as the acid. Lewis base, excuse me, donates electrons, and SO2 acts as the Lewis acid. It accepts electrons. All right. And notice that there's no water. In fact, that's a solid gas reaction. No water present. You don't need water when you're discussing Lewis acid bases. And in many cases, Bronsted-Lowry, you may not need water also. The only one that absolutely requires water is the other one. My mind's gone blank again. Let's see. Bronsted-Lowry, Lewis. Arrhenius. The Arrhenius definition requires water. Lewis doesn't require water. Bronsted-Lowry many times prefers water. Let's put it that way. Okay. 29. How about 30? Given the following values of pKa, determine which is the weakest base of the answers listed. Right? So each one of these is a conjugate base of some acid. That's what it appears to be. And as such, we can make a prediction about their strength as a base. So which one? Let's look at the definition. the weakest base. So these are all conjugate bases. Conjugate bases, and we want to know the weakest one. Right? So since the information that we're given is in terms of acid dissociation, what's the relationship? For the weakest base, what do we need? We need the strongest acid. So which one of these is the strongest acid? The one with the smallest pK is the strongest acid. HClO2, chlorous acid. So what would its conjugate base be? ClO2 minus. That would be the weakest base of this bunch. Wait a minute. All right. I fooled myself. If these were the only source of conjugate bases. But notice we slipped one in. That one right there. Cl minus. Derived from what? Strong acid. That would be the weakest base, Cl minus. Okay? I have to pay attention to my own questions. Under most circumstances, if Cl minus were not there, then ClO2 minus would be the weakest base. All right.
Hey, Dr. Blah.
Yes, sir.
I just joined back in. I was trying to answer a text message real quick, and I accidentally closed out of Zoom.
Oh, okay. Let me see if I've got everybody accounted for still. Let's see. 1, 2, 3, 4, 5. Yep, everybody's there. Okay. It happens. Let's see. I want to go to 38 next. There we go. Carbonic acid is a diprotic acid, H2CO3. So it's going to have two K values, two dissociations. The first one, let's just write it up here. The first one gives you this. The simplified version. And that K is 4.2 times 10 to the minus 7. That's Ka1. And then we take this one. And that Ka2 is 1 times 10 to the minus, 4.8 times 10 to the minus 11. Okay? And then we give you the Kw in there just so you don't have to look it up. So the question is, what is the hydroxyl concentration of a solution that is 0.18 molar in sodium carbonate? So the question is, what is this concentration? If 0.18 molar sodium carbonate. Okay? Now we got all our information up here. We got the question, right? What is this? So how do you get that from this reaction? These are not the reactions that are taking place. Actually, what you get is this goes into solution as those two plus this one. Right? Sodium's not going to react with water. It's a spectator. So the dominant ions, or the dominant species, while sodium is a dominant species, it doesn't react. Water is a dominant species, always there. And CO3 2- is a dominant species. So it is going to determine the pH. This reaction with water. Now the question is, ultimately, is that the only reaction that determines the pH? Right? If we take this one and react it with water, then we need the Kb based on that value, right? We calculate the Kb to determine this one reacting with water. But when we do that, we produce this one, right? So now we have this possibility. Is that going to be a significant determinant for pH? Well, look at the difference. 4 orders of magnitude difference. So it works the same way going backwards as forward. If we're going forward from the acid, this one determines the pH because it's -7 and -11 difference. If we're going backwards, then this one determines the pH, and that one then is insignificant. Now I can prove it to you, but let's do the calculation first, based upon that K and that reaction. Okay, so we're starting off with this one right here. All right, we need the Kb for the reaction of this with water. All right, we need this one plus water yields this one plus OH minus. Okay, so we need to calculate the Kb because the Kb is this one times that one divided by this one. All right, so what is the Kb? Kb sub 2, actually Kb sub 1, because we're going backwards. The Kb is Kw, 1 times 10 to the minus 14, divided by that. All right. So let me get my calculator out, my brand new calculator, and divide it by this one, 4.8 minus 11. Oops. There. .083 times 10 to the minus 4. All right. So that's the K for this expression right here. All right, let me write it over here. So I'm going to need this space. All right, so now we need our ice table. We got to find out what the equilibrium situation is in order to determine the concentration of hydroxyls. All right, so initially, what do we have? Initially, we have this concentration, right? 0.18 molar sodium carbonate, 1 to 1. For every one of these, you get one of those. So this one is 0.18 molar. Water doesn't count, right? Not in our calculation, let me put it that way. So what are you going to get? Well, the reaction's going this way, and you're going to have, you start off with 0, and the change then is going to be, you're going to have some of this, right? One of those, one of these. And you're going to lose the same amount over here. It's 1 to 1 to 1. So the equilibrium is going to be 0.18 minus X. This is X, and this is X. Okay. Now this is going to be equal to X squared, right? That one times that one, divided by that one. Now, can we eliminate this X right here? Let's look at the K value. With a value this large, and the X is going to be very small, right? Based on that, the X is going to be extremely small. So we can assume that we're approximately equal to X squared over 0.18. Okay. So that means 0.18 times this value, take the square root, is X. So let's see what that is. Let's see, I've already got that value in, so I'll multiply by 0.18 and take the square root. 6.12 times 10 to the minus 3. Molar. And that should be the concentration of hydroxyls. Right here. There. Okay? Now, do we need to prove that the second reaction here, this one, we're going backwards, going this one here. Do we need to take that ion from here and run the numbers? We can. You actually do get a contribution of hydroxyls if you use this value in a similar reaction where you have this one plus water yields that one plus hydroxyls. You get a value for hydroxyls. The thing about it is, the value is, let's see, the value is 2 orders of magnitude less than this value, which means it has no impact. If we have time, I can come back to this one and do the calculations. But in the interest of time, I think we ought to move on, because we haven't talked about buffers at all yet. And that's coming up next. Let's see. Let me set these aside for now and pull up chapter 15. Assuming there are no questions about chapter 14. Now, for this problem and problems like it, we were given a starting point, right, for an acid dissociation. In this case, we only need the ice table because we know where we're starting from. When we do, when we're talking about buffers and more advanced calculations, we may be introducing the concept of titration. That is, you're adding a base and an acid together in a certain combination. That gives you a different starting point. So that in those circumstances, you will let the reaction go to completion first. Then that gives you your starting point for the equilibrium part. So it's stoichiometry first, then equilibrium. But in this case, our starting point was already given. So that requires only equilibrium calculation. All right, so let's make some room here. And let's see, I'm going to modify just a little bit. 15. All right, I'll be back in 3 minutes. Bathroom break. If you need to, go ahead. I'll be right back. All right, I'm back. Okay, chapter 15. Now we're looking at equilibrium in depth, and actually we're on our way to buffers. Actually, that's the truth of chapter 15. Let's see. I want to cover one thing that's not in the document. I've talked about it before, but I just want to hammer this point home. It has to do with the titration curve. When you take we're going to use a weak acid to begin with, and do a hypothetical titration of that weak acid as we add increments of base, strong base. So we would have a graph like that, pH here, and we would have added base down here. Okay. Now let's suppose that we have a diprotic acid. Let's not make it too complicated, but I do want to get more than one proton out of this thing. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So those are our pHs. There. And let's say when we first put that acid into solution, and we can make something up, say it's 0.1 molar of a diprotic acid. Say we start off with, I don't know, in the neighborhood here, about 1.7 or so pH. Then we start adding base. And initially, it jumps up. Right? Like this. And then it sort of flattens out. Like that. And then once we get close to the equivalence point for that first proton, only for the first proton, then it'll jump up, and it might go as high as, I don't know, in that neighborhood. Then when it starts to flatten out again, you're extracting the second proton. Like that. And then when that second proton starts to run out, then it kicks off again. Now, this would be the first equivalence point at that volume. And this would be the second equivalence point at that volume. Okay, so we've identified the equivalence points, EQ1 and EQ2, corresponding to each of the protons, the first proton versus second. So what do we have down here? Well, at this point, we're right in the middle of that flat part. You have a ratio of what? The conjugate base of that acid. And that's equal to 1 right here. Right? That's the first buffer zone. And it occurs on this graph in the neighborhood of 2, 2.1, or 2.2 pH. All right? And that value right here is equal to pKa1. That pH is equal to pKa1 for that proton. When you get to this one, now you have a ratio of a different base, conjugate base of the acid. Right there, right? So this conjugate base becomes that acid for this proton. And that's equal to 1. Okay? Now that pH, about 8, is equal to pKa2. Right? So, in order to find the Ka for this proton, the second proton, you just take the antilog of the negative value. Same for this one. Antilog of the negative gives you the K for that one and that one respectively. Okay? So, when does the, at what pH do we reach equivalence for the first proton? In this case, it's pH 5. Right? So if you were looking for an indicator that would be useful for that equivalence and give you an end point near that equivalence, you would look for an indicator that had a pK of 5 for the indicator. That indicator wouldn't work for this one, right? Because it changes colors at that pH. So for this one, you would need a different indicator at about pH 10, pK of 10 for the second indicator. All right. Now there's some indicators that are mixtures. You could put this one mixed together with that one, and you could see when this one happened, would that color change? And as long as the color changes didn't interfere with one another, you could see the color change for this one, for the next increment of base. Okay. So, with this diprotic acid, you could create a buffer for two different regions. You could create a buffer for near 2.2, or you could create a buffer for near 8 pH. Either one. And that's what many life science type buffers do. They use phosphoric acid as the starting point, and then they adjust the phosphoric acid with addition of base, or by recipe, of course, to put it in either this region, or a third region, because phosphoric acid has 3 protons. So that's why phosphoric acid is one of the more commonly used sources for buffers for living systems, because you can adjust it either 3 different buffer zones. Okay, I just wanted to make that point. But those points, there were several of them there, weren't there? Okay, now we can get to the review document and look at specific questions. All right. So let me see here. The first one I have marked off as number 4. A weak acid, HF, hydrofluoric acid. Is that a weak acid? Yeah, as a matter of fact, it is a weak acid. But does it follow that that weak acid always has a low pH? No. In fact, I used to use concentrated hydrofluoric acid in the laboratory to help dissolve silicate minerals, because it's very effective at doing that. It's also effective at eating through your hand. If you just put get a little drop on your hand, so whenever I used HF, I always double glove. I have 2 gloves on each hand. You get a little bit of HF on your hand, and it's got a funny way of just reacting. It just keeps reacting until it goes all the way through to the other side. Anyway, this weak acid is in solution with sodium fluoride. Okay, so we've added both HF and sodium fluoride. And what does that look like? Well, sodium is a spectator, so we really only need to concentrate on the F minus, right? If they're in solution together, the common ion is F minus. So you have HF and you have F minus plus protons, right? That's the weak acid reaction that characterizes this buffer. So what happens when you add hydrochloric acid? Which ion will react with the extra hydrogen ions to keep the pH from changing, right? Well, let's say we got these added together as extras, right? So where do they go? Well, they fit into this reaction right here. So that means that these react with this one to produce that. Le Chatelier says that these extra protons are going to react with fluoride ion to produce HF, and that consumes a large portion of the extra hydrogen ions and leaves just a few behind, which means that the pH changes ever so slightly, but not very much. Now, why does it want to go back this way? Why didn't it just sit there? Because this is a weak acid, which makes a strong base. There's the conjugate base. A strong base picks up protons very efficiently, has a strong attraction to protons. So any extras you add to disturb that equilibrium are going to be picked up by that fluoride and sent packing. Okay, so the answer is C. The F minus ion is the one that reacts with the extra protons. While we're here, let's see, this was excuse me, number 4. While we're here, suppose we add base instead of acid, hydroxyls. What are the hydroxyls going to react with? Hydrogen ions. Make water. Now, why don't the hydroxyls just sit there? Well, look. Water is a very, very weak acid. 1 times 10 to the minus 14. Extremely weak. So that means hydroxyl is a very strong base. It goes after those protons with a vengeance. In fact, it goes after these protons more effectively than it goes after those protons, because these are free. Well, they're not really free. They're attached to water molecules, but they're more available. So we react that with this, makes water, and that consumes those hydroxyls. Now, what about these protons that we lost? The equilibrium shifts to the right to replace those. Many of them, not all of them, but many of them. And that accounts for the stability of the pH when you add acid or base. All right, so that was 4. Okay, let's see, what else do I have? I got 5 checked off. Let's take a look at 5. Which of the following is true for a buffered solution? How about A? The solution resists change in hydrogen ions. Oh yeah, it resists. It doesn't eliminate change. It only resists the change of in protons. So A is true. How about B? The solution will not change its pH very much, even if a concentrated acid is added. It's another way of saying A. It resists the change in pH. The solution will not change its pH very much, even if a strong base is added. That's also true. We just talked about that. How about D? Any hydrogen ions will react with a conjugate base of a weak acid already in solution. That's true. We just covered that topic in number 4 also. The conjugate base of HF was F minus. It's already in solution. So it will react with extra hydrogen ions added and consume them, convert them back to the weak acid. So all of these are true. All right, let's see. Let's skip down to number, let's see, I got too much paper in here. Skip down to number 8. There we go. We're going to do 8 and 9. So we'll just pull them both up here. So for 8, we have to look at this preceding statement. You have 2 buffered solutions. Buffer solution 1 consists of 5 molar acetic acid. That's the abbreviation for acetic acid right there. Okay. ACO is the abbreviation for acetate. Okay. Then you just add a hydrogen to it and makes it acetic acid. Let's see, I better put 8 up. Okay. And you also have 5 molar sodium acetate. Okay. So there you have the weak acid and its conjugate base, OAC minus. And they're in equal concentrations. which means what? We're right smack dab in the middle of the buffer zone. It's the ratio that matters. Remember? Anderson-Hasselbalch. When that ratio is 1 to 1, then you're in the perfect position for buffer. So if the ratio is the important part, concentration shouldn't matter. So if we have buffer solution 2 has 0.05 and 0.05 for each of those, it's got the same ratio, right? 1 to 1. So for 8, the pHs of the two buffers are identical. Let's see, the pH of buffer solution 1 is equal to that of buffer solution 2. Okay, that's nice. But they're still different, aren't they? They have different concentrations. So what does that mean? That means that the buffer capacities are different. In other words, there's a whole lot more of these to soak up hydrogens for the 5 molar solution than for the 0.05 molar solution. So the answer is C. How about 9? Let's see. 9, I think, is it's a different. It's not related to that scenario. So 9 is by itself. Which of the following is the net ionic equation for a reaction that occurs during the titration of nitric acid with potassium hydroxide? Well, you can either have it memorized or we can show you how it works. So if you have a reaction of nitric acid and potassium hydroxide, nitric acid, oops, has to be aqueous, potassium hydroxide yields what? It yields the salt plus water, K plus NO3, K NO3 plus water. Okay, do this back a little bit. All right, so what do we actually have in solution here? We have hydrogen ions, we have nitrate ions, we have potassium ions, and we have hydroxyl ions. What do we have on the other side? I have to write it down here. We have potassium ions, we have nitrate ions, and we have water. Okay? Remember how to write a net ionic equation? We got the molecular equation, the complete ionic equation. The net ionic equation, you just cancel the spectators. Here's a spectator, both sides. Here's another one. So what do we have left over? That's the net ionic equation for every acid-base reaction. Hydrogen ions plus hydroxyls yields water. All right. Okay. Let's see, that was number 8 and 9. 10. Let's look at 10. Number 10. In the titration of a weak acid, HA, so we got HA as our weak acid with 0.1 molar sodium hydroxide. The stoichiometric point is known to occur at a pH value of approximately 10. Right? So when we titrate it, that gives us sodium plus whatever and water. And the equivalence point equals pH 10. Okay, that's given. I like to write it up there so I extract it from the problem so you can see it more clearly. Which of the following indicators would be best to use to mark the end point of this titration? Right. If you know that this is the equivalence point, you want an indicator that will change color near that point, correct? And how do you know the pH at which an indicator changes color? It's near the pK of that indicator, right? Because the pK, the indicator is an acid, right? And it undergoes dissociation and reacts with the base as well, right? This reacts with the base, delivers its proton, and it has a K value or pK. Actually, let's write it like this: IN. And the color change as detected by your eyes depends upon the ratio of the conjugate base to the acid. Right? So the Henderson-Hasselbalch equation kicks in here, but for a different reason. Not to establish a buffer zone for the indicator, but to establish the color change ratio of conjugate base to acid. So that's why we look at the pK for the indicator as a clue to when that ratio determines the color change. Right? So we associate the equivalence point with the pK of the indicator. That's the connection. In this case, the best one in this case would be 11. It's the closest. The pK for the indicator would be 11, which would be close to 10. In fact, plus or minus 1 pK, plus or minus 1. That's the range for the pH of equivalence in your target reaction. And that's a general rule because the human eye detects a difference in color based upon 1 pH unit, either way. 10 times the hydrogen ion concentration, which would be 1 in one direction, 1 in the other direction. Okay, so that's number 10. Let's go down to 13. All right. Okay, we're still good on time. There we go. All right. 13. Which of the following solutions would be described as a buffer? All right, what are the conditions for making a buffer? The conditions for making a buffer means you have to have, in most cases, not all, but in most cases, a weak acid in solution with the conjugate base. Okay. So, which of the following would be described as a buffer? Well, let's see. What do we have to go on here? A is a weak acid and a strong acid. Weak acid, strong acid. Gonna get a buffer out of that? No, no, no. How about the next one? A weak acid and a strong base. Yep, that looks like a pretty good candidate there. Now the concentrations also matter. And what we've done here is we've combined this much base with this much acid, which kind of stretches it to the edge of the buffer zone, but still would work. What would be a better choice? If you put half as much base as you needed to neutralize it. Right? If you put 0.125 molarity sodium hydroxide with in equal volumes with this molarity of acid, then you would get a perfect base, perfect buffer, excuse me. But this is satisfactory. Sodium, how about this one? You got the salt of a strong, you got the neutral salt, right? Sodium bromide, sodium hydroxide, and hydrobromic acid. Strong base, strong acid, that's neutral. You add acid to it, it's just going to make it acid. It's not going to be a buffer. How about D? Ammonia, and sodium hydroxide. You got a weak base, which is a possible starting point for a buffer. But if you've got a weak base, you need a strong acid. Hydrochloric acid and ammonia, maybe, but not a weak base and a strong base. That won't work either. And the last one, let's see where we're going to put it. E. Strong acid, strong base, that's neutral. So B is the only one that comes close to being a candidate for a buffer. Okay, let's see, that was 13, 14. Which of the following mixtures would be classified as a buffer solution? Okay, so we're kind of beating this horse to death. So for 14, not only are we looking for the weak acid strong base combination, but we're also looking for the correct ratio. Right. So let's do A, B, C, D, E. Let's see if we can, test-taking technique, we can eliminate some things right off the bat. Let's see, here's a strong acid and a salt. No way you're going to get a buffer out of that. Let's see, there's a weak acid and a base, weak acid and a base, that could be weak acid and a base, weak acid and a strong acid. No, E won't work either. So it's either B, C, or D. All right, let's take a closer look at them now. Let's see, B, 50 milliliters of 0.1 molar acetic acid. That's another abbreviation for acetic acid, CH3COOH. The reason for that is CH3 is this group. Then it's combined with C with an oxygen like that. COOH. That's your acid proton. That's why it's written that way. Okay, back to B. So if we have 50 milliliters of 0.1 molar CH3COOH and 55 milliliters of 0.1 molar sodium hydroxide, what is that going to do when you add them together? You've got equal base. Actually, you have excess base to acid. You are past the equivalence point, right? They're the same concentration. So if you put equal volumes or greater volume of the base, then you've neutralized the acid completely. It's no longer capable of sustaining buffer capacity. So B is also wrong based on the titration effect. How about C? Okay, now we still got 50 milliliters of acetic acid. Now we have 25 milliliters of 0.1 molar sodium hydroxide. There you have only used up half of the weak acid, right? So you converted to this. You have consumed only half of those, which means you produce half of these based on that. So what does that mean? The ratio of this now to that left over is exactly 1. They're equal. That's perfect buffer. All right. We can stop there because we don't have any other multiple choices. But we can look at D, 50 milliliters of that acetic acid solution and 0.5 milliliters of a dilute sodium hydroxide. You're nowhere near the buffer zone there. You've got to convert more of this into that so that you have, roughly equal amounts. Then you have a buffer. So D, B is not it because it exceeds the equivalence point. D is not it because it doesn't get anywhere near the buffer zone. So that's why C is the answer. All right. 14. I just did 14, didn't I? Yeah, 14. Let's see. Let's go to 19. Let's see. 19. There we go. I skipped one up. We might come back to that one right there. We'll see. 19. All right. Consider the following indicators and their pH ranges. Each one of these, methyl orange, methyl red, bromophenol blue, phenolphthalein, alizarin yellow, they have different useful pH ranges for their indicators. And notice that they're not exactly plus or minus 1 pH from the middle. And that's because plus or minus 1 pH is sort of a rule of thumb. And exact measurements give you a slightly different useful pH range. So we're actually given that here. Okay, assume an indicator works best when the equivalence point of the titration comes in the middle of the indicator range. Okay, that's given. Which of the following titrations would methyl red be the best indicator? Well, in order to determine that, we need to know what's the equivalence point. Correct? So let's look at methyl red. Methyl red is 4.8 to 6. So it's going to be slightly acid. we want one of these reactions to reach the equivalence point in the acid range. So that's what we're looking for. Which one reaches equivalence in the not extreme acid, just slightly acid, like in the neighborhood of 5.5, 5 to 5.5 pH. Okay, so how do we do that? Well, we do that first by eliminating the obvious wrong answers. If you're going to combine a strong acid with a strong base, in A here, the equivalence point there is going to be exactly 7, right? Because when you create a salt from a strong acid, strong base, if you dissolve that salt in water, you get a neutral pH. So A can't be it because its pH is equal to 7. So this is the equivalence pH. Okay, let's see if we can find any others in here that are just way off. Let's see. If we titrate aniline, which is a base, right, with a strong acid, we get an equivalence point in the acid range. Okay, so B could be a possibility. Maybe. All right, we'll come back to that in case we have to break a tie. How about C? This base and this acid, that also produces an acid range. Maybe. How about HF and sodium hydroxide? Right? Weak acid, strong base. The equivalence is going to be basic. Right? So D can't be it. How about acetic acid and sodium hydroxide? That's going to be basic also. So it's a tie between B and C. Well, it's not. We need to break a tie. Let's say that. All right, so how do we break the tie? Well, notice that when you titrate this strong base, this weak base, both of them are weak bases. Remember when we tried to indicate the pH of a salt formed from two different weak components? We compared the Ka and the Kb. Well, in this case, we're comparing the Kb here with a very low, actually a very low pK, but a very high acid K. So the one that is the strongest base will pull the pH into closer toward the basic range. So if we actually start off with a weak base here that's stronger than this one, let's see, I'm not explaining that very well. Let me back up. The other thing we can do is the actual calculation. Now that we know it's a difference between B and C, we can actually do the calculation. And in fact, I think that's what I did. Yeah. Up to this point, we've been using logic. Now we need to break a tie between B and C. So we could pick one, right? Pick B, calculate the equivalence point pH. And if B's not it, then C has to be it. Or we can pick C and do that one. I don't know, 6 of one, half a dozen of the other. Flip a coin. C. So let's take C and say, what is the pH going to be at equivalence? Well, in this case, we need to do the let's see. We're going to titrate ammonia with hydrochloric acid. True? Ammonia with hydrochloric acid. So we get this one plus that one. Okay? Now, we're going to let this titration go to completion before we calculate the equilibrium pH. So if we got 0.1 molar here and 0.1 molar there, right? Then at equilibrium, the volumes would be equal for each one. So let's just make it easy on ourselves. Let's say it's 100 milliliters. Right? So that would mean 10 milliequivalents. 10 milliequivalents. And we're going to use up both of them, and we're going to produce 10 milliequivalents of this one. And, well, that was not going to react. Right? Chloride, once we produce chloride, it's not going to react with anything because it comes from a strong acid. It makes a weak base. So we really are focused on this one. So 10 milliequivalents divided by 200 milliliters, right? 100, 200 would be what? Would be 0.05 molar ammonia. Okay. Let's see. You know, that's not working out. I mean, we can do it this way, but it's not the most efficient way to it's not the most efficient way to do this, to answer this question. What if okay. Let's go ahead and do it. We've come this far. So this is the stoichiometric part. Now we have this yields this plus that. And we have initial concentration of this is 0.05 molar. And this is 0 and that's 0. Approximately. Then what's the change? Well, we're going to produce some of this and that and minus this. And we're going to have 0.05 minus x. This is x and this is x. All right. So now I got to erase this. Sorry. What's the K for this one? Well, we're given KB, 1.8 times 10 to the minus 5. This is Ka. There's acid making a conjugate base and hydrogen ions. So we need the Ka for this reaction. 1.8 times 10 to the minus 5 divided into 1 times 10 to the minus 14. Uh, 1.8 times 10 to the minus 5 equals what? .56, 10 to the minus 10. Okay, so that's the Ka. Oops. for this reaction. Okay, now that Ka is equal to x squared divided by 0.05 minus x, and that's such a small number, that x is going to be gone. X squared divided by 0.05. Right. So 0.05 times this number, take the square root. That will be the hydrogen ion concentration at equivalence. 5.27 times 10 to the minus 6. So if that's the hydrogen ion concentration, what's the pH? We'll take the negative log of that, right? Just take the log of it. And so here it is. Change the sign. 5.28. Okay, back to the original question. The indicator that we're aiming for is methyl red. Methyl red, 4.8 to 6.0, right in the middle. So that's why C is the answer. You could do this same calculation for aniline, and you'd find out that the pH would be lower. Is that true? I'm curious. I'm going to figure it out. We got the same concentration, so we really only need to make substitutions in here. Right. So the Ka for aniline is 1 times 10 to the minus 14 divided by 3.8 times 10 to the minus 10. 2.63 10 to the minus 5. 2.63 times 10 to the minus 5 equals x squared divided by 0.5. 0.5. Okay, x squared now is that times 0.05. Take the square root. Is 1.17 times 10 to the minus 147. There we go. Oops. Let me do that again. Yep, okay. Then we take the negative log of that is 2.94. So the pH change for the aniline would be 2.94. So here's what it looks like to me. The stronger the base here, the lower the pH when reacted with a strong acid. Let me say that again. If this is a stronger base than aniline, then the equivalence pH reacted with hydrochloric acid is going to be a higher pH. Right. So the weaker the base, the lower the pH for the titration. All right. That took a long time to answer that question, but it is what it is. All right, that was 19. 19. Let's see what else I got marked off. 23. We got a half hour left. 23. 23. Here we go. All right. 50 milliliter solution of 0.035 molar hydrocyanic acid, with that K value, is titrated with 0.0333 molar solution of sodium hydroxide. What is the pH of the acid solution after 15 milliliters of titrant have been added? Okay, this is fairly straightforward. It's along the same lines as we did before, but not quite as convoluted. So, what's the stoichiometric reaction? Hydrocyanic acid plus, and these are aqueous solutions, I'm leaving that out on purpose, sodium hydroxide. So the stoichiometry is going to give us sodium cyanide plus water. All right. So what are our starting conditions? Well, we've got 0.350 molar hydrocyanic acid. And we have, and there are 50 milliliters of it. Okay, let's see, there's another. I'm cheating myself out of a significant figure there. Sodium hydroxide is 0.0333 molar. And we're adding 15 milliliters of this. Okay, now we can calculate the stoichiometry, right? So initial and versus final. So when we're doing the stoichiometry, we do that in terms of absolute moles or millimoles, whichever the case may be. We only do equilibrium in terms of concentration. So how many millimoles of this? Milliliters times molar is millimoles. So 50.035 is 1.75 millimoles. Okay, initial. How about sodium hydroxide? 0.0333 times 15. 0.4995. 0.4995. And we got none of this and none of that. Right? So when we react these two together, since they're 1 to 1, all of this is going to be consumed. Right? So we're down to 0 here, and we subtract from that 1.251 millimoles. Okay, and we produce, well, actually, we do produce some of this. We produce 0.4995 millimoles. Okay, that's where it went. It went from here to there. So now we have a new starting point, but it's a different reaction, right? We've already done the titration. So now we have we have a reaction in which, let's see, I'm going to stay on target here. Right. Just checking myself. Now, we still have some of this acid left over. So we have an acid dissociation problem. So now that we have these values, and this is CN minus, right? Sodium is a spectator still. I'm going to leave that one up there and just write the new one here. There we go. So now we have 1.251 millimole and what's the volume, right? Now we need concentration. So we need the total volume, which is 50 plus 15 is 65 milliliters. And remember, millimoles divided by milliliters is molarity. It's 1.92 times 10 to the minus 2. Molar. This is the initial. Here we go. And the cyanide concentration is 0.4995 divided by the same volume. Right? So let's see what that one is. .68 times 10 to the minus 3. There we go. And this one is 0 hydrogen ions, right? Because the stoichiometry consumed all of the hydrogen ions in the process. Well, no, it didn't. No, it didn't. And I erased it already. Hold on a second. Shot myself in the foot. Um, 23. Looking at the wrong one. Okay, so we're counting hydrogen ions as 0 because we consume so many of them with sodium hydroxide. They're still, our starting point is still with the hydrogen ions here, so that's true. 0 there, this term, that term. Now what's the change? We're going to produce some of this, right? So we're going to get some X here, here, right there. That means it's got to come from here, minus X. And we're also going to get some more X here. So we have 1.92 times 10 to the minus 2 minus X. We're going to get 7.68 times 10 to the minus 3 plus X and then X. Okay, so there's our equilibrium expression. We just need the K value. Here it is, K, 6.2 times 10 to the minus 10 for hydrocyanic acid. All right, so now we've got 6.2 times 10 to the minus 10 equals this X times this value plus X divided by this value. There we go. Now, the question is, how big are those X's in relation to the term that they're right next to? I think in the worked problems, I went ahead and did the quadratic. Yeah. And the hydrogen ion concentration turned out to be much, much less than these values. So what we can do is we can say that one and that one are not going to influence this very much. So what we would say is X times 7.68 times 10 to the minus 3. Actually, that's approximate. And this is 1.92 times 10 to the minus 2. And we just drop these X's out. Now let's do the calculation and see if it comes anywhere near to what we'd expect. And we're looking for the pH. Right? So once we find the hydrogen ion concentration, we still have to convert to pH. All right? So we're going to say this times that divided by this is equal to X. And okay, there's that term. Then multiply by this 1.92 exponent. Oops. Let me start over again. 6.2 exponent. Okay. 1.92 10 to the minus 2 is times, and then 7.68 exponent to third power, negative third power, divided into that. And you get 1.55 times 10 to the minus 9. Right? So that value is much, much less than these if we can trust it. So let's take the negative log of that and find out what the pH is. 8.81. Yep, there it is. Now you can take this value here and plug it in here and here and here, and is it equal to that value? Let's do that just to check it. So 1.55 10 to the minus 9. And then I need to add to that 7.68 exponent 3 times. And then I need to subtract that value from 1.92, 10 to the minus 2. And then this one again times. And I did something wrong. I don't know what I did wrong. I tried to do everything in my head, and that didn't work. Well, I'm wasting time here. It will work. Try it on your own. That's 23. I've got one more, I think, and maybe just enough time to do it. Let's see, switch this over a little bit. There we go. The last one, 25. Right. A certain indicator has a pKa of 9, and a color change becomes visible when 7% of it is In minus. Is HIN is the indicator. In minus is the conjugate base of HIN. At what pH is this color change visible? All right. Actually, this one shouldn't take very long. So for the indicators, the reaction is weak acid dissociation. Like that. And it's going to make In minus plus the hydrogen number. Okay. What else is given? It has a pKa of 9. Okay. The color change becomes visible when 7% of it is In minus. Okay. So what does that mean? The color change is visible when 7% of this becomes that, which is what? The ratio is 7%, right? Now what that means? 7% of it is In minus. So the ratio is 7%. What's the decimal equivalent of 7%? Right? Well, we got extra zeros out here. Right? That's the fractional equivalent of 7%. So what does that look like? That looks like something we can stick into Henderson-Hasselbalch. Correct? pKa and this 7%. Right? Because that ratio is right here. So what's the pH? We should take the log of 0.07 and add it to 9. It's a negative number. 7.85. Okay. So what that says is, well, the nearest one is 7.88. At what pH is the color change visible? Now this is the pH color change coming in from the acid side, right? As you're gradually dissociating it, right? You're titrating it with a base. So it's coming up from the acid side, from the low end. From the other side, we'd have to be given a different ratio, right? For the top end. This is the bottom end. This is when the color first becomes visible in a titration with a base. Okay. So that's about all I have on this topic. Let's see if I'm leaving anything out. Nope. That's done. We did skip something earlier. We didn't actually skip it. I just thought we might be able to come back to it. But may have even been in the other chapter. I thought I put a little tick mark for that one. Nope, I did that one already. Covered it. So let's see about the buffers. Here. Let's see if I skipped anything interesting in buffers. I did mention this one. We don't have enough time to do this one. That's number 18. But it's worked out in the problems if you're interested in it. Okay, that's it. I think we've done enough for one day, and you should, if you understood everything that we're talking about today, if you can actually work these types of problems, then you should do fine for the exam. And we'll pick it up on Monday, next Monday, with solubility and complex ion formation. Just that one chapter. Okay, so we'll see you in a week if you don't have any comments or concerns.